Okay, guys. Did half of you leave for Christmas vacation already? So, who's going to be here on Thursday? Oh, basically, whoever is here today will be on Thursday. Okay. Then, today I will continue talking about linear algebra. So last time we rushed a little bit with the Cholesky factorization. And then on Thursday I will explain the next assignment. And I will give, so whoever is here will get some bonus. So I will try to explain thoroughly what the assignment is like, how to solve it. Ask lots of questions because what I do today directly reflects what you will have to do in the assignment. So last time we were talking about matrix A, which is SPD, which means a symmetric positive definite. And from here we wanted to compute a matrix L such that L times L transpose equals A. This is called the Cholesky factorization. And L is lower triangular. Okay, so and A is symmetric. Sure. In that case would be Hermitian, and then we would have such a decomposition where H is the complex conjugate. It would still be called Cholesky factorization. So here A is in R and here A is in C. Okay. And we also used gamma to indicate that A is an input, gamma is whatever operation, and L is the output. Gamma identifies the computation of the Cholesky factor L. And we went forward to see what the Cholesky factor looks like. We identified that the top left part of the Cholesky factor is the solution of another Cholesky factorization, in fact a very special one. So if we look at the matrix A, this is the input matrix A, we want to compute this output here, the matrix L, and what this partition here means is that if we look at the square here, here is going to be a 0 because this is a triangular matrix, and the contents of this portion here, that part here, contains the Cholesky factorization of A top left, and A top left is this portion here. Is this clear? And this is true for any such partitioning as long as A top left is squared. So in particular it's true when A top left is a 0 by 0, it's empty. It means that L top left will be 0 by 0. It is true if A top left is 1 by 1, in which case L top left is 1 by 1. And you can also tell me if A top left is 1 by 1, what is L top left? This is an easy one. Precisely. Then we have that L top left is the square root of A top left. Yes. Okay, and this is also true if we split the matrix in half, or if A top left is the full matrix, then L top left will be the full Cholesky factor. So clearly there is a recursive definition here. Then we notice that L bottom left is some triangular solve, so a linear system over A bottom left and L top left transpose. Okay, what does this mean? It means that this part of the solution, let's use a different color, okay, this relation here tells me that this part of the solution, which is L bottom left, is nothing more than a triangular system identified by A bottom left, which is this part here, okay, and what we just computed, L top left transpose. What is the shape? I believe that this is the shape, is A bottom, L bottom left equals A bottom left, L top left minus 1. So that's the triangular system that we have to solve. Okay, but regardless, the important thing is that it's a triangular system. And then finally, down here, we know that L bottom right is the Cholesky factorization of A bottom right minus L bottom left, L bottom left transpose. So, and this relation here tells me the contents of the bottom left quadrant, which is this guy here. L bottom right is now down here. And what this relation tells me is that I can compute L bottom right by taking the original contents of A bottom right, so this part here. This is A bottom right. I update this part with an outer product. This is a matrix times its transpose, so it's a special outer product. It's a circ, it's called a symmetric rank K update. So not only is it an outer product, it's a symmetric one. So I take this matrix, I update it by multiplying it, I update it by multiplying L bottom left times its transpose. I update all of these things, and then I compute the Cholesky factorization of all of that. Okay, so these are the relations. This is not an algorithm yet. And last time I jumped to an algorithm, and probably the jump was a little bit too long. So let's go through the same jump again, but making more steps. How could we start solving this problem? Well, we could, for instance, partition the matrix so that A bottom right is here, A top left is here, and A top left is 0 by 0. So if A top left is 0 by 0, you know already that A top right is you know already that is
0 by 0.
Thank you. A bottom left is n by 0, and A bottom right is the full matrix. This is the starting point. We have done nothing yet. So now we would like to do some work, some progress. How do we do progress? We follow this recursive structure. So we start slicing our matrix like this. So we expose, let's say we expose one entry. So this guy here is 1 by 1. This is n minus 1, this is n minus 1, and this is the whole remaining part of A. The whole thing is A. Okay? So we have exposed the top left corner of A. This here. And we have a relation, we know already that if we expose this thing, we can compute the corresponding L top left. So we can compute the corresponding corner in L. We just wrote it down. We know that L00, this first entry, is the square root of this entry here. Okay? So we have a way to start the computation. Since we have this little guy there, now we can solve the linear system to compute, to update all of this panel. So now we take this part of the matrix, which is A bottom left. We take what we just computed, which is L top left, and now we have everything to compute our L bottom left. Yes?
Can you show us this TRSM at this one-dimensional example?
Sure, I will on the computer. What this means is that we take A bottom left and we divide it by L top left. Remember, triangular solve is something like this. So we would invert the matrix, but of course we never invert the matrix. In the case this is a scalar, we actually invert the scalar. This is 1 over the scalar. We are allowed to do that. And so this is just a scaling of a vector. And we will do this in MATLAB in 1 second. So this thing goes in here. And what does it mean? It means that I have computed the full first column of my matrix L. So, and now that I have the top left, now that I have the bottom left, I can proceed and compute the bottom right, more or less, not really. I can at least compute this, I can update that. A bottom right we have, L bottom left we just computed, so I can certainly perform that multiplication. And what that means, it means that I can overwrite, I can replace A bottom right with A bottom right minus blah blah blah. So all of these we put it in A bottom right, we overwrite. So all this A gets overwritten. At that point, as I said, we have computed the first column of L, we have updated A, we can forget about what we did before, we can just proceed and slice another column here, and another row. And we can repeat the process. I would like somebody to complain because I'm skipping a step. I'm skipping a little step. Basically, I'm saying that now I can compute the Cholesky factorization of this matrix here. A bottom right minus that. Is that matrix symmetric? So the question is A bottom right minus, is this matrix symmetric?
Okay, A bottom right is symmetric because A is symmetric.
Yes, this is symmetric, it's true.
So and L bottom left times L bottom left transpose. Well, this is just the inverse of the other way of the Cholesky transformation. So
Whoa, 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 don't run so much. Just apply the transposition. It's a transpose of a product of the square matrix. these are not square matrices. I cannot do this. So forget about that. I cannot do that
Why not?
because these are, can I do that?
Uh,
So for the inverse I cannot do that. I need the square matrices. For the transpose, I guess I can.
I think it's for all kind of matrices.
Okay, I guess for the transpose I can, yeah, of course, the transpose I can do everything. So that becomes L bottom transpose, L bottom left transpose, transpose, because you always switch the order. So it becomes L bottom left, and then L bottom left transpose. Okay, so this matrix indeed is symmetric. It's the difference of two symmetric matrices. But the conditions for the Cholesky factorization was that the matrix was symmetric and positive definite. So the question becomes, is this object symmetric? Yes. Positive definite? Well, the answer is yes. I'm not going to prove it. It's actually fairly easy. But I'm not going to prove it. And this is indeed a symmetric positive definite. So I can start my second iteration with a smaller matrix. Okay? And I can just apply the same procedure, starting with this first entry, which computes this little element of the matrix L, the output. Then I will compute this column, which is the second column of the matrix L. And then I can do and perform another update, which means that I will update all this area here. And by the same theorem as before, this area here now is a symmetric positive definite matrix. So I can take another color and I can just look at, this matrix here. Forget about the first two columns, which I have computed already. Slice a new one, and so on. And this is indeed one algorithm. As part of your assignment, you will implement this algorithm, not this one. You will compute the Cholesky factorization in two different ways. I showed you one, and you will do two more, of course. Okay, so important thing is, right now at each step, I only slice one new column and one new row, which means that this entry on the diagonal is a scalar. And which means that every time I can simply say, okay, the solution is the square root of that scalar. The solution being the entry on the diagonal of L. In general, for performance reasons, you absolutely do not want to do that. And instead, you want to expose a set of columns and a set of rows. So we start from our matrix A. And instead of slicing just one column and one row, we go like this, where this object on the diagonal is B by B. And now we know this matrix is still called A top left. We know that A top left is a Cholesky of, thank you, L top left is a Cholesky of A top left. Now this A top left is B by B. So how do we solve that? Very nice, precisely. So now we do apply the algorithm above to compute just the to compute the first square here, or triangle, of the solution. Now this is b by b. Okay. This algorithm is called unblocked. So there are no blocks, it's unblocked. It means that it proceeds one column at a time, or one scalar at a time. This algorithm here, it's called blocked, and b is the size of the block. As part of the blocked algorithm, for sure you will use one unblocked algorithm. As part of the unblocked algorithm, you will go down to the scalar levels, so you will do square roots and such. In the blocked algorithm, you will use recursive calls to Cholesky, unblocked Cholesky, as well as other +3 operations, hopefully. So for instance, when we go and compute this, up there it was a TRSV, which means triangular solve with a vector, which means something like this, triangular matrix. This is our unknown equals our right-hand sides, so something like Lx equals b. This L has nothing to do with that L, it's just a triangular matrix. And now in the blocked variant, we have TRSM, triangular solve with multiple right-hand sides, which means we still have a triangular matrix, but now we have many right-hand sides. So this is now my question mark, and here I have my b's. So now I'm solving Lx equals b. X and b now are matrices, are a collection of vectors. This thing here belongs to +2, this thing here is +3. And I told you already, +3, much better for performance. Continuing, once we have done that and we have computed our L bottom left here, we can update all of this. In the unblocked world, we had matrix minus that minus L bottom left was one vector times the same vector transposed. In the blocked version, we have matrix minus a block times transpose, the same block transposed. And this is a +3, and this is a +2. So why do we go to blocked algorithms? To use +3. As part of as part of blocked algorithms, we have recursive calls to the same operation, but at the unblocked level. Okay. Questions so far? Yes?
Well, kind of a stupid question. Why are we thinking about this problem anyway? What's the big deal about Cholesky factorization? Why do we bother with it? Why did you take this problem?
Where can I delete? Okay. So, why Cholesky factorization? I want to solve Ax equals b. How do I solve it? Have you ever seen this? Sorry? It depends on A, yes. This is a linear system. A and B are our inputs, and X is what we're trying to compute. Of course, it depends on A. Let's say that A is just general. We don't know anything about A. Then what do? We write A as a product of two matrices L and U. Why do we do that?
Because it's cheaper to triangle L.
Thank you. That's a very good question. Sorry, that's a very good answer. If it's not square, it's not even a linear system. So sure. Let's assume that this is a square. If it's not square, it would be maybe a least square problem. All right. Now, if A is a symmetric, we don't need to go for LU. We can do something better, which is something inherently related to Cholesky. We would do LD, L transpose. Just take it. If A is SPD, you don't need to compute two matrices. You don't need to compute two matrices. You can just compute one matrix. This thing here is twice as fast as an LU factorization. That's why we do it. The matrix as a structure, we exploit it. I can give you 20 examples where Cholesky factorizations appear, and this is just one of them. Cholesky factorization is really, really, really important because in engineering and science, symmetric positive definite matrices appear all the time. Okay, maybe I will just give you one involved example that has nothing to do with linear systems, but instead has to do with eigensolvers. Okay, this is the next level up in difficulty. Linear systems, this is for babies. Eigenproblems, this is for macho men. So this is a generalized eigenproblem, so this is for real hardcore people. And B oftentimes is a symmetric positive definite. So what you do, you factor it and you go from a generalized eigenproblem to a standard eigenproblem. And this is under control. This is well understood. If you like these kind of problems, come back in 1 year in the summer. I teach high performance matrix computations, and it's all about this and that. But for now, this is too advanced. So, okay, other questions? No? So let's go to MATLAB. I want to show you what MATLAB is good for and what Mathematica is not good for. Okay, let's start off by defining an SPD, symmetric positive definite matrix. Maybe 4. We can do it from a random matrix. This is n by n. Then there are a couple of ways of defining symmetric positive definite matrices. For instance, these will be symmetric and positive definite. This is a possibility. The problem with this is that the condition number of the resulting matrix is the square of the condition number of A. Condition number is a measure to say how bad a matrix is, so you don't want to square it. So,
Positive definite.
sorry?
Why would it be positive definite?
Well, I'm trying to skip the numerical linear algebra details. Okay, you are asking for it. That's not the reason. A positive matrix doesn't have to be positive definite. So, quick detour. Okay, it's here. I guess this is the corner of the detours. Quick proof that that is a symmetric positive definite. First of all, I give you a matrix is a symmetric positive definite if and only if X transpose X A is greater or equal than 0, and in fact is a 0 only if X is a 0. So 1, and 2. Okay? So a matrix that satisfies this relation for any x is a symmetric positive definite. And now I tell you, I suspect that this is a symmetric positive definite. Symmetric, we know that is a symmetric. Let's put a y here and a y there. Now, this object, let's call it x transpose. This object is x. And this is an inner product. It's very likely to be greater or equal to 0. And in fact, it's most likely it's 0 only if the vector x is a 0. So this tells us that AA transpose is symmetric positive definite. Okay. Other proof, the eigenvalues of a symmetric positive definite matrix are all positive. And here we go. Not that this is a proof, but it could be just by accident. Okay, different ways of creating a symmetric positive definite matrix. This is a symmetric matrix. This is nowhere near enough to be positive definite, but now I add some big numbers on the diagonal. What am I doing? I'm creating a diagonally dominant matrix. If you don't know what that means, that's perfectly fine. But this is a different way of creating a symmetric an SPD, with the exception that this matrix is very well conditioned. So we're going to use this. By the way, I believe that for our experiments, since random is between 0 and 1, this might be SPD2. Yeah. It doesn't matter for us. Anyway, now we know this matrix satisfies our requirements. So we can run our algorithm on this. What I will do, I will compute Cholesky with MATLAB Cholesky. Okay. So this is what MATLAB gives me. Let's see if it's true that this is a Cholesky factorization. So the product of L times its transpose should be M. I subtract the product from the original input. I compute the norm. We want this to be? Please. It cannot be 0. It's floating point numbers. It should be? Yes, something of the order of 10 to the minus 16. Very nice. Let's do it again for something much bigger. Oh yeah, sorry. Yeah, in this case I really have to do this. And 1. Okay, so very good. Okay, since I want to show the output, let's do this and that. So we have M symmetric positive definite and L is our solution. But we don't cheat, we want to compute L ourselves. Why? Because that's what you guys will do for your next assignment. So, how do we start? We have an SPD, it's all for us, and now we want to tackle it. How would you guys start? Yeah?
We implement the non-blocking method?
Sure. That sounds like a good idea, yeah? How do we implement it?
First, we need to create a new function file and then,
Okay, I will let,
one,
sure,
and then
1 second. I will let you guys implement functions. let's just go through the steps. So the first operation, what would it be? Square root sounds good. So my L 1 1. Do you agree? I am computing. Oh, maybe I should initialize my L. My L will be 4 by 4, lower triangular, and the first entry, so the top left entry, will be the square root of the corresponding entry. Okay, so no. Can I already check whether this is right or wrong? Is it possible? Can I do this? Do I have a reference? Yeah.
We can check if this tangent strand pose is equal to the top left element in M.
Yeah, this is probably true, but let's see if MATLAB computed the same quantity. We have MATLAB's answer, so far so good. We didn't do anything stupid. Okay. So L for now, oh no, my L is a little bit small. Let me expand my L. Okay, now we have to fill these three guys down here. My L. Suggestions?
A is the same index divided by L11. Yes,
Okay, I agree with you. And we have a first column of the solution. Let's see if MATLAB is doing the same thing. Yeah, we can see it already. No, we cannot. Mm.
Shouldn't it be double backslash instead of the forward slash?
Ah, really? Does no? No, this is a scalar. This would make a mess. Oh, it's not A, it's M. Okay, looks much better, huh? So we have computed the first column. So far, so good. How do we proceed? This is gone. Ah, here. How do we proceed? We did something, then? We shift, yes. Before shifting, we need to do something. We update. Thank you, guys. Update. And I showed that the update is this vector times its transposition, times its transpose. We have to take these three elements. We have to transpose them, and then we have to update the M portion of the corresponding portion in M with that. So M of minus thank you. Then what? The same thing transposed. Okay. And now we have updated M bottom right, so we have shaded that part of the matrix. We can now move on. What's next? What? Shift, okay. Computation, tell me. We do shift, you're absolutely right. We are at the pink, or yeah, let's say pink stage. Yeah, absolutely. You're absolutely right. But tell me what computation I want to do. What do I want to compute now? 1 second, 1 second. My L22, yes. Thank you. Oops, sorry guys. Okay, same story as before. Oh, okay, L is here. We're looking at MATLAB's Cholesky. We're on the right track. We're doing the right thing. Now I have to update this part of the matrix. And how do I do that? We go here. Now we go from 3 to n, second column. 3 to n, second column. This should be the 2, 2, what we just computed. And we look back at L. And we are still right. Getting lucky today. What do we have to do now? Update, yes, the bottom right part of M, which means this quadrant there. So it's 3 to n, which is whatever is sitting there. Now we take what we just computed times its transpose, we update. Next iteration, square root. And yes, it's still good. Then we take from 4 to n, from 4 to 4, this is just one entry. Just dividing. We're still pretty good. And now I have to take this object, multiply. So I have now to update only the bottom right element of the matrix M. Okay, I have to take this, and this. And what I'm doing, I am taking this entry here, I am multiplying times its transpose, which is itself, so I'm squaring this element, and I'm taking this entry in the matrix M, and I'm subtracting the two. Is it done?
What you just said, it's a cell.
It's a what?
It's 1. With multiplication, the scalar of the transpose is 1, right?
Sorry, I don't understand. What are you saying? I am taking this entry here, my L, 4 to n, n is 4, so...
Between transposition and inverting.
Ah, yeah, transposition. So I squared it. Now I have updated M. Am I done? No. Thank you, very good. I need the square root of the last one. This is my L, this is L. So we are done exactly the same computation or something very similar to what MATLAB does. I hope you guys followed, because you will have to do all of these steps yourself, but not like this step by step, in a much cleaner way. Now, before I continue with this, I want to show you some horror story. So, with which environment? You have seen that I like Mathematica, right? So, let's do the same story. N equals 4. Okay. Then, let's say random, real. How is it? Something like n. Of course not. Random, real. Rule or list. What does he want? I can never remember random.
Yeah, for arguments.
Range. Aha. Okay. So this. Okay. We have a 4x4 matrix of random numbers. Now we have to create our SPD. So I'm lazy, so I'm going for this. Let's just check whether this is real, positive definite. All the eigenvalues are positive, so yes. Okay, we're good. We have the input matrix that we want, matrix M. And now we want to compute L. First of all, let's compute L. There is something called the Cholesky factorization or something like that. Not Cholesky, Cholesky decomposition. So we start off with the wrong foot. It returns only the upper triangular part. So I didn't say. We can compute the Cholesky factorization also with the upper triangular matrix. In that case, you would have U transpose U equals A. So you can decompose the matrix either as a product of lower triangular matrices or upper triangular matrices. And Mathematica just chooses the upper triangular one, even though I want the lower triangular. There is no way to let him know that I want the lower triangular, so I just do this. Transpose. And just to make sure that this makes sense, norm L transpose minus M. Okay, this is pretty accurate. So far, so good. Now let's compute our L. We have to initialize it. My L 1, 1. By now we know this is the square root of M 1, 1. L 1. Let's put them together. L 1, 1. Okay, so we have computed the right quantity. Now what do we want to do? We want to update the first column. No, update, sorry. We want to compute the first column of L. So here we want from 2 to n, column 1 equals corresponding part in M divided by okay, and let's compare right away with Cholesky. Did I do it again?
What's the difference between one semicolon and two semicolons in the access price?
Thank you. I don't know what this is. Thanks. Not that it helps. Okay, comma 1. This helps. Thank you. So far, so good. So it looks like MATLAB and Mathematica are doing the same thing. What do we have to do now? Sorry? Update, yes. So tell me how to do this update. Now we want M. We want to update which part of M? Yes, so give me the indices.
2 to n. 2
To n. Okay, so this is the bottom right part, very good. This is going to be itself minus, what happens next? Thanks. Yeah. Of the same object. The first two levels cannot be transposed. What do you mean? What did we do wrong? I mean, we did it collectively, I'm pretty sure, and we have done it already. Why would this be wrong? Okay, let's look piece by piece. Does that object make sense? Yeah, oh no. Where is it? What? Oh, okay, because of course now there is the transpose. So it actually updated it with the stupid transpose. Anyway, believe me, this is not the problem. The problem is not in this part. The problem comes from here. Actually, it was complaining about the transpose, so what's wrong with this? Let's look at that. Yeah. We have a 4x4 matrix. And we are trying to access this vector here, this column, piece of a column, to then transpose it and compute something like this. We access this object, and for some reason, Mathematica decides that it's a list. Ta, ta, ta. It's just a list of entries. It's not a column, because Mathematica doesn't distinguish between columns and rows. So,
because the Mathematica just, when it takes the 2 to n, comma 1, just puts it as a list, and it's manual.
absolutely, you are absolutely right. That's exactly what it does. it just took those 3 entries and created a list out of it. It didn't think that this list is coming from the column of a matrix, and maybe column has meaning in linear algebra. It just created a list. So what do we have to do to
For the transpose, you just make a
map thread? Okay, yeah, we can do. Map.
transpose, you make a vector.
You are on the right track. So let's do this. We put this list inside another list, and now we transpose that. Can I just copy? Well. And now this really looks like a column. This is perfectly fine. Now we transpose that, and what do we get? We get just this. So if we take that and this, and this is the update that we actually wanted to compute. So if you go in matrix form, do you see the problem? We wanted to transpose the second part of our expression. It's a column times its transpose. And here, this thing does, we are forced to do exactly the opposite. We are forced to build an object when we already have a column, and then we are forced to transpose the left, the first element. We are not transposing the right. I mean, this is exactly the opposite of what the math is telling us to do. This is a true horror story. So whenever you have to do this kind of computation, you can see my opinion on which tool is probably better. Okay. And as for the assignment, there will be the first part to be done in MATLAB, and then a second part to be done in Mathematica, but 2 different problems. It would be cruel to ask you to do this in Mathematica. So let's go back to the board. And I am trying to give you more hints on how to implement this. So what I tried to jump at last week was the fact that even though it looks like we work on 2x2 matrices, actually everything that we have done comes from 3x3 matrices. We started off our iteration by splitting a matrix, let's say like this, doing some operation, something else. Then we split again, operation, something else, and so on. Okay? But we never really discarded the part that we have computed. So our history, we never really created a new, smaller matrix. We always worked inside the big matrix. So how do we do that? We start saying, let me partition A in 2x2, A top left, A bottom left, top right, bottom right. And I initialize this by saying that A top left is 0 by 0. So basically, I start off the computation by saying A top left is empty. I have done absolutely nothing. All of the work is in A bottom right. A top left will contain the solution, what we have computed so far. A bottom right will contain what we still have to do. Then we have a while loop that says, okay, please continue until A top left is not equal to size of A. Okay, I can say L top left. I am skipping steps.
We can say that until A bottom right is not equal to 0, it's easy.
That too. What I'm doing here is I should have something for the matrix L as well. Okay. So, let me rephrase. L top left contains what we have computed so far, as well as L bottom left. And A bottom right is what we still need to compute. And what we want to do is to make L top left grow as much as the whole matrix L. At that point, L top left will be the full matrix L, which means will contain our solution. So how do we do this? As I said, at the very, very beginning, A top left is empty. So I want to expose something. So now I go to a 3 by 3 partitioning. So now I really need the colors. I start from a 2 by 2 where this is empty. And I go to a 3 by 3 where the purple stays the same. So this is still empty. But now I expose new parts of the matrix. In total, I have a 3 by 3 object. 1, 2, 3, 1, 2, 3, 1, 2, 3. What was called here A top left, now I call A0, 0. What here was called A top right, now it becomes two objects. See, this is now two objects, is A01, A02. What was A bottom left now becomes two objects. A10, A20. And what here was A bottom right, now it's four objects. And these are the objects on which we were operating. Our algorithm was okay, we have something entirely similar for L. Where this is purple. L10, L20, 1, L2, 1, L2, 2. Okay, our algorithm told us that L11 equals square root of A11 if A11 is a scalar. If A11 is a block, we add that L11 equals Cholesky of A11. Agree? Then our algorithm told us how to compute L21, TR as V, or TR as M. And then we would have to update A22 with jar. Actually, it's symmetric, so maybe it's I don't remember. I think it's here. not circ, cir. Yes, circ. Thank you. Is it circ? Damn. So. Now we go and we read some BLAS. Beautiful. Beautiful. This is it. You see, this is a non-symmetric update. I don't know if you can see it. Maybe I should. Here we go. This is a non-symmetric update, x times y transpose, and here is the symmetric update, xx transpose or xx Hermitian. So this is it, and cir, okay, and circ. So I was right. You guys are tricking me. Yeah, this is a cir. And this is a circ, which only makes sense because this is a symmetric rank k update, where k is the width of the update. And this is a cir, which is a rank 1 update. Okay, this is the algorithm, computation. But then we want to move forward. So what do we have to do? We are in this 3x3, we have this 3x3 object, and the objective is to make A top left grow, expand. So now we have to push what we have computed into L top left and L bottom left. We want these objects to grow. So what do we do there? We say A00, A10, A20, A11, and the same for L. Let's see what happened. We started with A top left that was empty. Everything was in A bottom right. We have a split A bottom right so that we have exposed some diagonal object, A21, A22. We have worked on A11, A21, sorry, the same on L. Everything that we do on A, we do the same on L. We have worked on A11 to get L11. We have worked on A21 to get L21. See? And then we have updated A22. At this point, we want to move these bars. We want A11 and A21 to go to the past, to the history. And how do we do that? Over here, we group these four guys and we push them into, see, we group them and we push them into A top left. Basically, top left has just acquired A01, A11, A10, has been padded and has grown. A20, A bottom left, which was all of these objects here, now has become A20 and A21. So it has gained a new column. 1 second. A bottom right, which was these 4 entries, A bottom right has lost A11, A21, A21 and A12. A bottom right has lost them, and you see that A22 now becomes A bottom right. So now we call A bottom right only this object here. In the end, A top left has grown, A bottom left has grown, A bottom right has shrunk. Yes?
So the big idea is that you introduce new variables.
Yes. There is really no big idea, it's just a way of abstracting from the indexing. If you remember in MATLAB, I always have to keep track of which iteration I was in. Here, I don't have to keep track. A bottom right is always responsible for what comes next. A11 will always be the diagonal object on which I compute. A21 will always be the panel, and A22 will be always the remaining part. The exact same framework, the exact same structure works for most numerical linear algebra operations. If you want an LU factorization, you traverse the matrix like this. If you want any other Cholesky variant, you will traverse the matrix like this. You want to solve a triangular system, you do this. You want to solve a triangular system with upper triangular matrix, things are a little bit different. Yes, precisely. Now we don't use the bottom, we use the upper part, and also we don't go in this direction, but we move in this direction. What it means that we would initialize the matrix like this, where this object now is empty. And then how do we repartition? Like this. And we magically move in this direction.
Basically, replacing the zeros with n's and then going back to the zeros.
Yes.
And it's the same, even we don't have to flip, it's flipped already.
You do have to flip. No, you do have to flip, because now, so at the beginning you would have that A is partitioned as A top left, A bottom left, A bottom right, and A bottom right is a 0 by 0. But then when you partition, now A top left will be partitioned into 4, and here A bottom right was partitioned into 4. Now you partition this side, which is A top left. So yes, these things are switched. And for the assignment, I will give you 2 algorithms for the Cholesky factorization written in this format, and it's up to you to code them up in MATLAB in the most elegant way. Questions? No questions?
No, okay.
No questions.
Just the left side was unblocked, right side was blocked, and everything applies to both variants. And
Yes.
it's all right.
The big difference is that A11 on the left side is 1 by 1. It's a scalar. On the right side is a B by B block.
So as the block size, we just choose randomly, or
So in high performance computing, you choose the block size so that these matrices fit in cache. You want these matrices to maximize the performance, so normally you choose something like 192 or 220, something like this. The truth is that anything above 10 or 20 is much better than an unblocked variant. So as long as big is 20, 30, 50, you will see already a performance benefit. If you will experiment with matrices of size 1000, you can already have A11 size 100 or 200, and you see that these are worlds apart. These are completely different worlds. You will see this. Okay, guys, I'll see you on Thursday, and on Thursday we will try to take it easy. I will explain to you what I want for the assignment. I will explain both parts of the assignment. The MATLAB, you have a sort of an idea already. I have to cover the Gram-Schmidt or orthogonalization to be done in mathematics. Okay, see you on Thursday.